Louis de Broglie proposed in 1924 that particles can behave like waves in addition to behaving like particles. We see the wave nature of electrons in electron diffraction, and this is the same idea as light diffraction, the double slit experiment where we saw a single source of light going through two little slits, and it created this pattern on the box. That can happen with electrons too. What's really kind of hard to get your mind around, because we think of electrons as particles, is that this interference pattern is not caused by pairs of electrons interfering with each other, but a single electron interfering with itself. Right? What? Electrons are not miniature baseballs. Sometimes they behave that way, but other times they behave like light does. They are waves. So here we have electron diffraction. So you need some sort of an electron source, and you're shooting the electrons at this barrier that has two different slits. What is observed is an interference pattern on the detector screen. This interference pattern is very much like the interference pattern seen with light in a double slit experiment. So this was proof that electrons have wave nature. This came in 1927. If electrons only behaved like particles, what would particles do? I mean, you could think of this as being two windows and you're throwing baseballs. Well, if it's particles, if the particle hits the hole, the slit, it'll go through. If it hits the barrier, it doesn't go through, right? And you get two lines here from electrons that got through. But what we actually see is this, where there's an interference pattern caused by the electron waves interfering with themselves as they go through. Wave nature is an inherent property of individual electrons. An individual electron can behave like a wave and like a particle. This is that superposition where it's in two states at the same time. It's a particle and it's a wave. De Broglie came up with a relationship between wavelength of a particle and its velocity. So this is known as the de Broglie relation. You don't need to memorize that, but it would be given to you, and you'd need to know how to do calculations. This is the mass of the particle, and that's the velocity. That's an italic V. It looks an awful lot like a nu. Sorry. Lambda equals h over mv. So h is Planck's constant. Again, you don't need to memorize that one, but need to know where to look for it. So 6.626 times 10 to the minus 34 joule seconds. So we can do a calculation. We can calculate the velocity of an electron that has a de Broglie wavelength approximately the length of a chemical bond. Assume this length to be 1.2 times 10 to the minus 10 meters. So they gave us a number in there. So let's write that down. So that was the wavelength, 1.2 times 10 to the minus 10 meters. And de Broglie wavelength, so that should make us think, oh, we might need to use that de Broglie relation. So that's Planck's constant over m times v, the velocity. Well, Planck's constant, we can look it up, 6.626 times 10 to the minus 34 joule seconds. We're trying to find v. What else do we need? Bless you. We've got lambda, we've got h. We're trying to find v, we need m. M is the mass of what? of an electron. Well, I don't remember that. I asked Siri yesterday. It didn't go so well, but I'm going to try it again. Hey Siri, what is the mass in kilograms of one electron?
Okay, I found something on the web for what is the mass in kilograms of one electron. Take a look.
Let's see. Well, that's better than what I got yesterday. Okay, so 9.109 times 10 to the minus 31 kilograms. 9.109 times 10 to the minus 31 kilograms. That's the mass of one electron. Really small. So here we've got this equation. We need to solve for V. So one way to do that is we could cross multiply, get rid of the fraction, and then we're going to divide by lambda m on both sides. Those cancel out. We end up with the velocity is equal to Planck's constant divided by the wavelength times the mass. So let's fill in our numbers, including the units. H is 6.626 times 10 to the minus 34 joule seconds. Lambda is 1.2 times 10 to the minus 10 meters, and the mass is 9.109 times 10 to the minus 31 kilograms. Now, the units look pretty messy there, don't they? So we've got joules and seconds in the numerator. We've got meters and kilograms in the denominator. Well, a joule is equal to a newton times a meter. A newton is a kilogram meter per second squared. So if I take joule out and replace it with a newton is a kilogram meter per second squared times a meter, and I've got this. The kilograms cancel. One of the meters up there cancels this one. This second cancels one of the seconds. I end up with meters per second. Now, you don't have to know how to do that. When we're dealing with messy things like joules, kilogram is the base unit of mass for the SI system. So if you've got things like joules, seconds, meters, kilograms, the units should work out. It's great if you know how to do that, but not absolutely necessary. Okay. 6.626 times 10 to the minus 34. Divided by 1.2 times 10 to the minus 10. Divided by 9.109 times 10 to the minus 31. Getting a really big number here. 6061770.41 meters per second. Looking at all of the numbers that I'm using here, the sig figs are limited by the 2 sig figs given in the wavelength. So I want to round this. We need to be careful because you can't round, 6 million to 61, right? That's not cool. So we should probably use scientific notation for this. So we want to keep 6.1 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6 meters per second. The velocity of an electron. Is that a reasonable amount? In general, large things move slowly, small things move quickly. Just think about football players, right? The big guys on the line are kind of slow. And it's the smaller guys that are fast. Electrons are very small, so it's reasonable that the speed of the electron is very fast. This is a high rate of speed, 6 million meters per second. Nobody's car can do that. But it's still slower than the speed of light. Any questions? Yeah.
What's the speed of light again?
3 times 10 to the 8th meters per second is the speed of light. So that's a little less than 2 times slower than the speed of light. So the uncertainty principle, and this was hinted at when we talked about Schrodinger's cat and the superposition. When you open the container, the cat is either dead or alive. When you try to observe an electron, you cannot observe its wave nature and its particle nature at the same time. You can observe one or the other, but you can't see both of them. The evidence for its wave nature is the interference pattern. Bless you. The evidence for its particle nature is its position. So in that slit experiment, the diffraction experiment, it's which slit is the electron going through? Because as a particle, it can only go through one slit. Particles can't be in 2 places at the same time. Waves can, but particles can't. So we say that the wave and particle nature are complementary properties. The more you know about one, the less you know about the other. So if we took that diffraction experiment where we're shooting electrons through these slits and we shine a laser beam across here, the laser beam would allow us to detect which slit the electron is going through. You turn the laser beam on, diffraction pattern goes away, and you get 2 bright spots. The electron is behaving like a particle. Turn off the laser, the diffraction pattern comes back. What? Isn't that crazy? I mean, it just blows my mind. You cannot observe it behaving as both at the same time. It'd be really cool if we could, but we can't. Any questions about that? Heisenberg's uncertainty principle sort of quantifies this idea. I won't give you any problems about this on an exam, but they could show up in a homework question. So this is saying delta x times m delta v is greater than or equal to h over 4 pi. Delta x is the uncertainty in the position of the electron. Exactly where is it? Delta v is the uncertainty in the velocity. How precisely do we know the velocity? So is it very uncertain? Or are we really close in on what the velocity is? M is the mass, and then here we've got Planck's constant over 4 pi. I have no idea how he came up with this, but it works. The important thing is the general idea here. If our uncertainty in the position is very small, then the uncertainty in the velocity must be very large. If this uncertainty is small, that uncertainty must be large. We can't know both things at the same time. We can pinpoint where the electron is, but then we know nothing about its velocity. Or we can establish how fast it's moving, but then we can't say anything about where it actually is. Or we could know a little bit about the position and a little bit about the velocity, but you can't know both of them at the same time. Electrons are ornery little critters. So classical physics, which is the physics that I like, We've got particles moving in a path, and that path is determined by the velocity, the position, and any forces that are acting on the particle. That's called determinacy. The present, things that are going on with it right now, determines what happens in the future. I throw a baseball, and what I do with it right now determines where it goes in the future. With the electron, we can't know the position and the velocity, so we cannot predict the path that it's going to follow. This is known as indeterminacy. You cannot predict the future based on the present. We can only predict it statistically. So it's kind of fuzzy. The best we can do to describe the probability that an electron will be found in a particular region is using statistical functions. We can get a probability distribution map, and that's the best we can do. So this is classical physics. Baseball player hits a ball. It's got a trajectory. If we look at it at this point, we can say this is exactly where it is. We can measure the velocity, the direction that it's heading in. We can observe the force pulling on the ball. There's wind resistance. All those factors can be put together, and we can predict where the ball's going to land. Now, the amazing thing about your brain is that even if you've never learned anything about physics, you can predict where the ball's going to go. Some people are better at it than others. But little children playing with balls, their brains are learning how to predict the path of an object. How does a baseball player in the outfield move and get under and just in the right spot to catch the ball? His brain is doing all these calculations. It's amazing. We understand things like this. Electrons aren't like that. So here, this would be classical physics again. Here we've got a pitcher pitching a ball. And he can pitch the ball in exactly the same place every time by doing the same thing. Or you can think of setting up a pitching machine. And it shoots the ball with the same velocity in the same direction, and the ball lands in the same place every time. Right? Nice and predictable. If you do that with an electron, it's going to land in a different place every time. But we can't know its velocity and its position at the same time. So, hopefully it's going to roughly go towards the batter, but the best we can do is a probability map like this, where there's a 20% chance it's going to land in the center. If we expand that circle, 40% chance out here in this circle, 70% chance it'll go through that circle. But it could hit the ump in the head, right? It would go right between the bars. It could hit him right in the face. It could do that. It could hit this lady up here. We can't predict exactly where it's going to go, what it's going to do, because we can't know its velocity and its position at the same time. We can do statistics. Here we can look at the number of pitches and the distance from the center of the strike zone, and we see that, aiming that electron at the center of the strike zone, that it hits the center more frequently than it does far away, but we can't predict exactly where it's going to go.